Hello back. In the last video we wanted to tune hyperparameters, but we drifted into the direction of environment selection and how stochasticity and determinism of environments influence the results. Sparked by a discussion in the Stable Baselines repository about which environment to best use for benchmarking results, HH0RVA1H had a look at my work and showed me some mistakes I had made in this discussion. And it boils down to different action spaces and different default frame skips. Of course, you can find that in the documentation, so be very aware, depending on which version you choose, you not only have the deterministic versus stochastic frame skip indicated by the brackets, you also have a different action space. Meaning the same action might mean something different in the different environments. So if you train on V4 but apply the model to V5, it might just confuse some of the actions. And specifically it's about going left and right, which is 3 and 4 in the full space and 2 and 3 in the reduced space. So if you train your model on this reduced space, it cannot perform well on the full space. Based on this insight, I created a new code set, 4.1 PPO environment comparison, in which I trained the model 3 times on the 3 different environments, V4, V4 no frame skip, as well as V5, but with the same action space, and I then evaluated these models on all the other 3. I tinkered a bit with the evaluation callbacks code, so that one model can be run in 3 different environments for the evaluation at the same time. And the blue line you see in these graphs is the model that was trained on the deterministic environment, and you see it performs well on the deterministic environment on the right upper side, but it performs poorly on the other 2. Whereas the models that were trained on stochastic environments, the orange one and the red one, they both perform well on all environments. With that out of the way, we can finally focus on some proper hyperparameter tuning. Here you already see the results of this work. There are about 100 different trials that have been run, and the point I want to make here is that I have implemented a bunch of different metrics to evaluate them. Up until now we had the mean reward as well as the episode length as a logged feedback from the evaluation callback. And here you see we have added a bunch more, like the median, the standard deviation, something I call conservative reward, which is mean minus alpha times standard deviation. So if you set alpha to 1 or 2, you get, assuming a normal distribution, you would get a specific quantile. And I have implemented also the rank reward, meaning the nth worst episode. So if we have something like 30 episodes we evaluate on each run and set n to 7, it would be something like the lower quartile. You can find this implementation in the trial eval callback, where I modified the standard evaluation callback. I just copied the code from the evaluation callback from Stable Baselines, and in row 161 and following you will see where these new metrics are calculated. Just, median using the median, the rank reward using the partition function, and so on. And after that they get recorded into the logger. This is the standard logger, and this piece of code up here is also new. This is where I allow for an arbitrary name choice. So if you have several evaluation callbacks you want to run at the same time, you can do so, and they don't override each other because they have separate namespaces. This was necessary when I wanted to look at the evaluation of one model in 3 different environments at the same time. Now, the codes we'll be looking at are the ones starting with 4.2. The analyze features one is the one we use in the end once the study has been optimized, all the trials have been run, where we investigate the results and make the nice contour plots. The define study one is where we add trials manually to the study, which I have done a lot because I wanted to investigate specific parameter combinations. And the execute optimization is one that I've run multiple times on different machines in order to do some parallelization. And what's important for the parallelization to work is that you have a central database in which Optuna can save the different trials and can basically coordinate between the different code executions. So instead of using an SQLite database as before, I've now used a MariaDB in the background. So there are multiple workers that all access the same database, and the database makes sure that they all access a consistent set of information, that there are no kind of race conditions with file access, but each time a worker asks for a new trial to be executed, that it can be done in coordination with the other workers. That was a great idea, but it didn't work, because it became apparent soon that the parameters go a bit in the direction more is better, eating up more and more GPU memory, and I only had one machine left with enough memory to run a trial. There are some slight changes in the create objective function. You will find it when you scroll down. It's where if a environment is selected, this function ensures we choose consistent parameters for this environment. This is based on the discussion on the issue that I had mentioned before, where the action space would be a different default for version 5, where it would use the full action space by default, which makes the game unplayable. If a model is trained on v4 and is asked to play on v5 and it has a different action space, it cannot perform. The other piece that is done here is if we have stochastic frame skip, that it's using the same frame skip on average as the other environments. Now, before we dive into the results and see how different hyperparameters affect the scores, the median or the mean, let's have a look at the code which is used for learning a PPO model to get a bit of a better understanding of what these hyperparameters actually mean. And I've just taken one of the older versions of our code, the 1.3, and I'm using the debugger to step into the .learn. And let's have a look what is called when we go in. And we're here in the PPO .learn function, which itself just calls the super.learn, which means it calls the learn method from the class from which it has inherited. And once we step in, we see we are in the onPolicy algorithm learn function. There's a while loop over the different time steps, and within that while loop, it's calling the rollouts. Now when we step into the rollout function, we see it's saying collect experience from the current policy and fill a rollout buffer. And the length of the rollout buffer is this n rollout steps, which we have filled with n rollout steps equal number of steps. So don't confuse the number of steps here with the one that is iterated over in this while loop. But this will be the size of the rollout buffer is basically how long do we let the model play around, or how many steps do we let it play the game in order to step up the next learning iteration. And you will see that in this collect rollouts, it also resets the rollout buffer. So basically each time this collect rollouts, it's just letting the game play for another n steps. After it has collected the steps, it then calls the train method, which is not in the onPolicy algorithm, but in the PPO class which inherited from this. And within the train function, we see that there is a for loop over the number of epochs. So the rollout buffer is filled with the number of steps, and then based on this kind of recording of the game, the model will be updated a bunch of times, and this bunch of times is the number of epochs. And you see inside the for loop of the epochs, there's another for loop that iterates over the rollout buffer and always takes a certain batch size. So there is this rollout buffer of many steps, and from that randomly drawn are specific steps that are then used for the update of the model. And that is defined by the batch size. There's a comment here which says do a complete pass on the rollout buffer. So I'm assuming what this means is that it's without putting back the individual elements of the buffer. So it will just iterate until it has gone completely through the buffer. So we should also expect that the batch size is smaller than the number of steps, which will not be the case. Even in our baseline, where we copied the parameters from the zoo repository, we see that the batch size is 256, whereas the steps is 128. So let's run our baseline through the debugger and see how it behaves in that section of the code. So now we're at the same place again, where it takes packets of the batch size, and let's see how often it iterates over them. But first let's check the batch size, 256 as expected, and the number of steps is 128. So the rollout should only have a size of 128. Now what happens becomes more clear if we set another breakpoint and look into this function. And we will see that it actually takes the buffer size, which is the 128 from before, the number of steps that we have taken, but we multiply it with the number of environments. So actually we don't have 128 steps, but we have 1024 steps overall. And we have a batch size of 256. So this for loop should execute 4 times. So let's check that. So we're at the first execution, at the second execution, the third, the fourth, and it goes back. So we need to remind ourselves that the number of steps is to be multiplied by the number of environments, and then the batch sizes are taken out of that. Now, with having this very rudimentary understanding of what these hyperparameters do in the model, let's have a look at how they affect the results. The first picture we see when we run the analyze features code is that is the hyperparameter importances, which hyperparameter within the range that it was allowed to change it had the biggest influence on the median reward after 1 million steps. And keep in mind that we evaluate in the V5 environment and not necessarily in the one where the model was trained. So the train environment also has an influence, but we already see that the 3 most important ones are the number of steps, the number of epochs, and the batch size. Now we will dive a bit deeper into the first 3. I'm aware that batch size has about the same effect as frameskip and train environment, but I think the first 3 belong together from a conceptual point of view because they interact a lot within the training code. So let's look at these 3 in separation. And we see the contour plot for them with all the different variants that the different trials that Optuna has calculated. And we see that a lighter color has a higher value, so a higher median reward after 1 million steps. What we can immediately see is on the right side that a high number of steps or a high number of epochs does not necessarily perform well. So just throwing more at the training doesn't work. Now let's zoom into the picture where we have the batch size versus the number of steps that we're taking. And what you immediately see is that there are a lot of very local maxima and minima. Sometimes they're the maximum is very close to the minimum, like we see here around 3,000 in the lower part of the picture, as well as 3,500 with a bit of more steps. One issue is that the other hyperparameters are not kept stable in this picture. So, this one might be with a different environment than the other one. So in the code you will find a function called subset study that I use to make a plot that only includes trials where all of the other parameters are kept stable. So I'm not really using Optuna for its full potential, like finding sampling its own optimal trials for the next investigation, but I actually make more of a grid search. And you can compare this here in the picture that says all. So all of the other hyperparameters are not kept stable compared to this one where I set epochs to 4 and a bunch of other hyperparameters are also keep stable. So of course it's much less points, but it also seems to be a bit more of a less noisy picture. Now, when looking at the number of epochs and optimizing that parameter, we see some very clear maxima around 6 and 8 epochs. I was not sure about this because it seemed like a very, very local maximum. It was also the reason why I introduced the other metrics on the evaluation callbacks, because I thought maybe it's kind of an outlier in the calculation of the mean, but this is happening on the median as well. So when looking at TensorBoard and looking at how the mean and the median would choose the same trials, we actually see that our top two trials, the green one and the orange one, which are trials number 63 and 51, you see here the 51, it just appears and goes in both of them. It's in both the second place, and the 63 is the top place in both. So that would not make a big difference changing the metric. Now, since I switched from SQLite towards MariaDB, I'm using a different tool to look at the database. I'm using dbeaver, and I've created this, this query. Be aware that the system attributes table, which provides all of these parameters as in a JSON format, is only valid for manually added trials. So it will show nulls for any trials that the sampler has generated. For that, you would need to connect the trial_params table. I sorted the trials by value, so this is the median score, and you see the top two have the same configuration, just the same one run twice. You see it differs by about 10 points, and number 3 and 4 are the same and they differ by 2 points. It's basically the batch size 3000 with 6 epochs versus 8 epochs. And below that there come some slight variations with different number of steps, with half of them, or with 2000. A batch size of 2000. So it seems quite convincing that the optimal choice is in this region. And we will now run the best configuration for a bit longer, for more time steps. In the last section I cheated a bit by just setting the learning rate to linear. As we only ran it for 1 million time steps, it didn't really matter that much. But when we want to run longer trainings, it's likely advisable to reduce the learning rate during training. In stable baseline Zoo, we saw that they're using a linear scheduler, meaning the learning rate scales linearly towards 0 once the training is finished. So we had a learning rate in the beginning of the training, starting here, and just went down linearly to the number of steps which we predefined. So let's say we set 1 million, then the learning rate would look like this. If we would train for 10 million, so I'm using a log scale, then it would look like this. And here is the problem, that even if all of the other hyperparameters are the same, you will not see the same result in the training curve, because even during training at an earlier step, 2 different learning rates were used. So this is what I would call, it's not scale invariant. What I want to achieve instead is that we have a curve that is independent of whether we stop at 1 million or whether we stop at 10 million steps. And all the points are the same for both learning rate schedules, and it will always have the exact same point as long as it's below the 1 million. The learning rate at a particular point in time does not depend on the number of overall time steps. Now the corresponding implementation you can find in the create objective schedule file, and there's a function called exponential schedule which takes in the initial value and the distance to be trained, so the 1 million or 10 million steps, and a delta which I'm going to motivate in a second. and it hands back a function that can serve as the scheduler, which itself just takes the remaining progress and calculates the learning rate out of it. So we are looking for a function for our scheduler, and we already know some boundary conditions for it. We know it should start at a given point, we call it y0, and after the training, so after something like 1 million steps, and we call that the distance, it should be at a point y1. Now, with an educated guess as this function being an exponential function, it's straightforward to derive how the delta would look like. I ended up with two slightly different implementations of this scheduler, one taking in the target value at end, so the y1, and the other one taking in the delta. The issue was a bit that if we take in the target value at the end, then we need to mentally distinguish between the distance in which we want to train now and the distance in which we want to measure the target value at the end. So if we change from training for 1 million steps to 10 million steps, we would also need to adjust the target value at end accordingly. And well, since I'm lazy and I didn't want to do that, I actually changed the function to take in the delta itself, which stays constant and produces the same function independent of the distance for which we train. I ran a bunch of hand-selected trials in the Optuna framework to determine the best scheduler combination. Now, what you see here, the red and the blue one, are from the 4.2 exercise, the one we just had, where we have optimized the parameters, and the two strongest trials we had were 51 and 63. So this is what we're aiming to be able to reproduce now with a scheduler that can run for a longer time. And let's first see how that compares to the baseline, which we have including the prediction, including the aimbot. And we see now if we look at all of the trials with the different schedulers and with different learning rates, with different clip rates, and with different deltas, we can even far outperform the results, the previous results. We can get up to a score of 150 within 1 million steps instead of, well, something like 3 to 4 million steps from before. This is on the rollout scores, which is on the V4 environment, which we also train. Now let's look at the evaluation environment, which is the breakout V5. And you see it doesn't look that great. We went up to 150 with the V4. Now we get up to almost 100. Now let's say 90 in V5, which is, well, still significantly better than what we had before the hyperparameter tuning. Now we're taking a step back and look at our former baselines. We have the blue line, which is the model including the aimbot with the hyperparameters from stable baseline zoo, and the orange one, which is just the hyperparameters from zoo but without the aimbot. Now, our methodology changed slightly, and I had rerun both of these setups in with the evaluation environment set to V5. You see the red line corresponds to the blue one. It's slightly worse, but you can still assume it's from the same model. And the lighter blue line is the longer training without the aimbot. And you actually see that it performs significantly better than the old one. For one, because we have trained longer, but it's also performing better, I assume, because of the training rate, because the training rate in the Chapter 2 just dropped very quickly to 0, whereas here we're training just significantly longer. With these two baselines in mind, the red one with the aimbot, the blue one without the aimbot, and both with the hyperparameter selected from zoo, we're going to add the run from the previous chapter, where we had optimized for the number of steps, the number of epochs, and the batch size, as well as the scheduler. And you see the optimized version just performs significantly better after 1 million steps. To ensure the setup is working correctly, I reran the same parameterization as the pink one and the green one, just on the new code set, and I get very similar results. So I tried to run this setup for a longer time period instead of 1 million for 10 million steps, and I saw that after 3 million it just went flat and it didn't improve anymore. To understand what's happening here and why this perfectly tuned model did not perform well in the long run, let's scroll down at the training metrics and let's look at the clip fraction. And we see that the clip fraction for this particular model after 2 million steps just rapidly drops off towards something very close to 0. So this is already a logarithmic scale. So my suspicion is that once the clip fraction reduces too much, there will be no more learning, because the clip fraction tells us when the model updates are clipped, so they exceed certain thresholds, meaning at that point the difference from one model to the next is kind of at its maximum in terms of how much the parameters have changed. Also, when we look at the learning rate, we see that it is already at 10 to the minus 5, which is something that only happens around between 9 and 10 million in the original model. So my assumption here is that the learning rate just drops off too fast. We have optimized the hyperparameters in order to maximize the score in the first million steps, but so for longer running trainings, we might want to increase our learning rate or decrease our delta such that the drop-off in learning rate is less severe. That is something I tried then in the next trial, where I decreased the delta quite significantly such that it, the learning rate is higher, significantly higher all the time. And when we look at the results from that, we see that in the beginning the orange line performs worse than the gray one. So our hypertuning was actually correct in selecting the gray one over the orange one, but in the long run the orange one far outperforms the gray one. So what I learned today is be careful in your hyperparameter tuning, especially with pruning. If you prune too early, you might get results that are good in the short run but bad in the long run. Looking at the clip fraction of our new model, we see it going to basically 0 after 6 million steps. And when we look at what this means for the scores, we could estimate that the scoring basically remains flat after 6 million steps. The hypothesis for the next step is that the scores don't improve anymore once the clip rate goes to 0, and the clip rate goes to 0 once we hit a certain lower threshold of the learning rate. And we're hitting that threshold at about 6 to 7 million steps, and we see the learning rate is 1e minus 5, and it started at 1e minus 3. So it's 2 orders of magnitude, it's once the learning rate is 2 orders of magnitude smaller, or 1% of the initial learning rate. This simple approximation sparked the idea of trial number 11, and which we see it ends around at 1e minus 5. It didn't run fully through because I ran into the environment needs restepping error from the monitor wrapper, and I was not inclined to just run it again. So we see that with the 3 new trials with the different learning rate deltas, we can achieve scores around 350, but it seems to really max out at that value. Maybe if we run it a bit longer, we can squeeze out another 10 or 20 points, but I'm not really hopeful with this approach to get beyond 400. On the evaluation side, the picture looks very much the same. We seem to max out with all 3 around 200 mean reward and something like 175 median reward. If we compare that to our previous baselines, we see that actually the previous baselines did not perform significantly worse than this. So the hyperparameter tuning was mostly affecting the results on V4 itself, but not so much on V5. Now we have trained models that can achieve 300 to 400 points consistently in a stochastic environment. There might be potential to achieve even higher scores by either running longer, tuning a bit more parameters, better model selection, And you can look at the folder 9_future, where I've dumped ideas that I tried, but they didn't work out so well. One idea was to have an environment wrapper that replays the final sequence where an AI failed. And it would replay that several times to just reinforce this last piece of the learning a bit more. And it would, on reset, not always go back to a fresh start, but sometimes draw from some saved states in order to make sure that the learning experience is more balanced over the whole realm of the game and not only focusing on the beginning all the time. Another idea was to have some repeated hyperparameter tuning, so not only tune in the beginning but also tune after 1 million steps, after 10 million steps, and so on, because I have the suspicion that the optimal hyperparameters change with the progress of the training. And that would kind of culminate in the idea of a continuous tuning of hyperparameters. And I tried to have a continuous tuning of the learning rate by having a second environment on top, and the second environment's action space would be changing the learning rate, and it would be played by another PPO on top of the core PPO. And this meta PPO would then control the learning rate and observe how the learning rate has influenced some of the metrics that are saved to the logger. I think all of these ideas have potential, but maybe Breakout isn't the game to get started on them because of the constrained resources. I hope you enjoyed the videos and see you back soon.